pattern. Let me just explain it a little bit. When a canal was designed, suppose it was expected that this much area is there, this much area is there, flow area will be there, and sediment deposition has taken place, so its capacity has reduced. Now its sectional area remaining is only this much because of sediment deposition. So when the capacity reduces, then suppose we expected that this much water will be carried, but it will not be carried. This is one point. Well, that we could understand. But if scouring take place or erosion take place, then what is the problem? Well, if the canal was designed like that and scouring has taken place, so the canal has taken a shape of this one. Now, with a given discharge, earlier it was expected that the water will be flowing at this level. Now we know that in a canal, if we expect that this is the water level, then water level, with this water level, it can move up to, say, okay, there will be a slope here, and with this water level, it is moving up to certain depth, up to certain distance. Here, depth will gradually come down, and it is moving up to certain distance, like that. We can show more explicitly this point, that if we just draw a slope like this, and then depth is like that. So here we have, because from a river, okay, let me draw it here. See, from a river, this depth in this side will always be higher. And then generally when we do irrigation, suppose from here we are collecting water and then we are supplying in this side. So to what extent we can go? This canal is moving like this, and at certain extent we can go. And this side, that what is the command of that canal? A command of this canal means to what extent this canal can carry water. Now this, if the canal size increases, then the flow depth, which was earlier expected to be at this level, will come down to this level. And once the flow depth come down at certain point, then the distance to which it can travel will also reduce, because the this bed resistance, size and everything changes, and then its head reduces. Total head, as we know, that it is depth of flow meters. It is Z plus depth of flow plus V square by twice Z. Here, if it is scouring is occurring, Z value is coming down. Earlier, suppose Z value was up to this much. I mean, from here, say piezometric head was up to this much level, Z plus B, P by W, or Z plus Y. But now it will be only this much. So head is coming down, and when the channel is expanding, then velocity will also drop. So this V square by twice Z, that portion is also dropping. So total head is reducing. And when you have less head, it can flow up to lesser extent. It can flow up to lesser extent. So the command of the canal is reducing. Command means the distance or the area that can be covered by a particular canal is called the command area of the canal. So as it cannot carry water to far distance, so its command is reducing. And so when we expected that, we had an expectation that we will be able to cover this much of area, but once this scouring occur, we will not be able to cover that area. So both erosion and deposition has the problem. And because of this problem, people had to start thinking that can we have a channel section which will neither be subjected to erosion or it will not be subjected to sediment deposition. And that forced the investigator and engineers to start thinking on this particular line. And several shield theories are therefore developed. And most popular of those are, say, Kennedy's shield theory. And it was suggested by R.G. Kennedy in 1895. And most interesting point here I would like to mention that again another shield theory, or that is called Lacy's regime theory, that was proposed by Lacy in 1939 after a gap of about more than 40 years. So it was suggested. And both these theories were developed in India. These are, say, Kennedy was also an engineer in that field, in a field that is in a irrigation system that is called Upper Baridua Canal System. And that was in Punjab, of course, this now in Pakistan, that place is. And now there he was engineer, and then he was experiencing this problem that I have explained. And because of this problem, he then started observing that if there is, if it is possible to have a stable channel, that's why his theory is always said as the theory of stable channel. And then from the entire canal system, he was trying to find some channel reach which are remaining stable or which are not changing, which are not getting affected by erosion and deposition. So he first took those channel portion which is actually stable portion, and then he tried to observe in those stable portion that what is the secret of that. Well, and he observed the flow velocity in those channels, and then he was trying to see that this flow velocity, at this flow velocity it is remaining stable. Now then he tried to think that this flow velocity, is it related to, of course slope is always there, and then the slope was very not that steep slope, these were mild slope at that portion. And then he was trying to see that whether this velocity is coming from, or whether this velocity can be related to the depth of channel or width of channel, like that he was observing. And he could later see that for that portion, this velocity, achieving that velocity is depending on the depth of channel. The reason he suggested is, of course, like that, that erosion or scouring take place because of the, say, when the water is flowing, it has some frictional resistance with the bed, and because of that bed resistance, there will be eddy formation, vertical eddy current and eddy formation, and then vertical eddy will basically lift the sediment, and then that is responsible. And for this phenomenon, depth is more responsible, which is more responsible for the eddy formation on the side. So, and he, according to him, he observed that this side eddies are not creating that much of problem or not that much of responsible for carrying the sediment, and that way he could relate, by observing these things, he could plot the velocity and the depth graphically, and then he could derive a relation which was quite satisfactory for that portion. But of course, it was a very site-specific study. It was for Upper Baridua Canal region, and then the formula he adopted became very popular, and it was known as Kennedy's formula, and it was used for design purpose. But when it was applied to some other area, then Kennedy also later could realize that no, the width of the channel has something to do with this, and this particular, for the silt characteristic of the Upper Baridua Canal region, only his theory is valid. For other silt characteristic, because silt will have to, the silt characteristic will have to have some important influence on the entire erosion process. So for other reason where the silt characteristic is different, his formula is not giving that stable channel as he expected. So later on, of course, different investigators started working on that, and this formula was modified for incorporating all these possible influence of other factors. And still now also this formula is used. Of course, nowadays Lassie's formula is also used, and some other formula like semi-empirical, or we can call the analytical approach of tractic force, is also used for design purpose in India. Well, we'll be discussing all those in more detail in our next class. Thank you very much.
Hello everyone, in this video we'll see about Kennedy's theory. Kennedy's theory is mainly for unlined canals, and it is used only in India and other regions around India. It is not used in western parts of the world. So what is an unlined canal? Unlined canal is nothing but when the sides of the river and banks and everything, they are left as such. Here everywhere they will be surrounded by soil only. But whereas in lined canals, you will provide something like a concrete coating here. So which will help in preventing seepage and all that. And it's quite costly to provide lining. So in most of the cases, we leave the canal like as it is, but still you have to design it. So this empirical design was proposed by Mr. Kennedy, which he tried some experiments in the Barry-Dope canal system. So what happens in an unlined canal? So I'm just drawing the cross section of the canal. So when the water passes, some of the particles which are there gets settled. So water always carries some particles along with it. So if this is the bed, there will be particles down and also in the banks of the canal. So this water, it rubs against the sides of the wall and also at the bottom. So because of which some solid particles get broken and these are carried by the water. So that is known as erosion. And these eroded particles, suppose when the velocity drops down of the water, these particles slowly start settling down. That is known as sedimentation or silting. So what are the disadvantages of this? When lot of silting takes place, it keeps on filling this. So the effective depth reduces. So the capacity reduces. And if suppose excessive scoring takes place, that is erosion takes place, these keep on get removed. So the whole bed gets eroded and the cross section keeps on increasing and a small canal becomes like the width becomes very large, because of which the depth reduces. And if the depth reduces, the height, the head of water reduces. So there is very less energy, and because of which it can command only less area. Suppose water is at a very much height, it can easily irrigate a lot of area. But if it is suppose of a lesser depth, let us say half of this, it can irrigate only half the area probably. So this is a very bad thing. And so Kennedy proposed in such a way that erosion and sedimentation balance each other over time. So that is the whole concept of Kennedy's theory. So if you design a canal such that silting and scoring does not take place, it is known as a stable channel or a regime channel. So what does it tell exactly? The exact definition goes like, whatever silt which is carried by the water should always remain in suspension. They should not settle, and also the water should not erode further particles. So whichever is carried should be carried all over. So that is what a stable or regime channel means. So the velocity should be such that it should not erode the bed, nor it should allow settling. If suppose the velocity is very less, particles settle. And if suppose the velocity is very high, whatever particles at the bottom, they get eroded. So the velocity should be in between these two. And that's what a stable or regime channel tries to achieve.
Get started with YouTube Creator Academy. Learn how to set up your channel and upload videos with ease.
So what Kennedy did was he carried out research in this Barry-Dope canal. He selected places like where the silting or scoring does not take place at all. So for last 30 years, the silting or scoring did not take place at certain sections of the channel. He selected only those sections and tried to come up with an idea why it is not happening. So he came up with this theory. When a water is flowing, Suppose this is the bed of the channel and water is flowing. So when water is flowing, what happens is it rubs against the bed. So there is a friction which is happening. This water rubs against the bed, so friction happens, and because of which vertical eddies are formed. So eddies are nothing but it is a swirling motion. You might have often seen this motion where when the water rubs against the bed, this kind of energy forms, like the water swirls up. So when these swirls are formed, it helps keep the silt in suspension. So whatever silt which is there, it helps keep it in suspension. So this vertical component of eddy, that is a force. When eddies are formed, there is an upward force. So vertical force pushes the particles up. So whichever particle which is below, because of the swirling motion of water, it goes up. That force brings it upwards. And because each particle has a weight, it again goes down. So again the swirling motion is formed, and because of these two processes, it's always kept in suspension because of this eddies. So our whole idea should be that the velocity of this channel or canal should be just enough to produce this eddies. That is known as critical velocity. At a certain velocity only these eddies get formed. So that velocity is known as critical velocity. So the velocity of the channel should be greater than or equal to critical velocity. So what Kennedy did was he carried out various experiments on that sections of the channel and came up with an empirical formula where he told critical velocity equal to 0.55 d power 0.64. So this is the depth of the water in the canal. So he related critical velocity only with the depth of the water, as he assumed that these vertical eddies are formed only from the bottom, and he ignored the eddies which are found from the banks of the river. So if you generalize this formula, it is C into depth power n. So he gave C is 0.55 and D is 0.64. But the drawback with this formula is it was applicable only for the Bari-Doab canal. But this silt which is here will have various sizes in various canals, and it will have different properties and gradation, etc. So he could not apply the same formula elsewhere. So that's when he came up with a more generalized formula where he introduced critical velocity ratio, which is m. Critical velocity ratio I am writing as CVR. So this m varies from canal to canal. Obviously for Bari-Doab canal, m is equal to 1. Because that's where this whole experiment was carried out. And for other canals, you can apply this factor m, which varies from 0.7 to 1.2. So this m, if it is finer than, if the silt is finer than this Bari-Doab canal, m value is less than 1. And if it is coarser than this Bari-Doab canal, it is greater than 1. So this m increases with coarseness of the silt. That is, if the size of the silts keep on getting bigger, m increases. A simple logic to this: if the If the silt is coarser, that means its weight is more. So if the weight is more, it will easily try to settle. So there should be a very large force by the eddies to make it go up. So if you need a large force, you obviously need a greater velocity. So if you need a greater velocity than this V naught, m should be greater than 1 for coarser particles. So that is the logic here. Let us see how we design based on these theories. So what you should do is, first you should take a trial depth. Let us say you just assume the depth of 1 to 2 meter. You can just assume any depth, or it could be greater also, it depends. So first you start with the assumption depth. Let us say it is 1.5 meter. And based on the formula which you just saw, you determine the critical velocity. V naught equal to 0.55 m d power 0.64. So you substitute this d here, and you may also know the critical velocity ratio for that channel, and you determine the critical velocity ratio. The discharge of the channel also will be given, or you may have to assume accordingly, and you also know the V naught, so you will find the cross-sectional area. Again, one more drawback in this, you have to assume the slope later on. So you just find out the cross-sectional area for now, and later you decide the slope, etc. accordingly. So now you have got the cross-sectional area. So you should determine the actual velocity for this cross-sectional area and depth. So this actual mean velocity you will measure. Actual mean velocity is nothing but the velocity of the water keeps varying with depth. At the bed, because of so much frictional forces, it is almost 0. So at 0.6 depth, if suppose this whole depth is 1 meter, at 0.6 meter, whatever velocity of the water you get, that is known as the actual mean velocity. So you use Cutter's equation to determine this actual mean velocity. Cutter's equation goes like, it's a very big formula. V is equal to 1 by n plus 23 plus divided by S n root r, and this whole thing is multiplied by root of rs. R is nothing but the hydraulic mean depth, which is area by perimeter of that channel, and S is slope, as you know. And N is rugosity coefficient. So depending on the channel condition and discharge, it varies from 0.02 to 0.03. If the channel condition is very good, it is at a lower value. It also depends on the discharge. Depends on discharge and channel condition. If the channel condition is very good, it is towards 0.02, and if the discharge is less also, it is towards 0.02. Usually Cutter's equation is used to determine actual mean velocity. Sometimes you use Manning's equation also, which is quite simpler than this, which goes like this, and N is the Manning's coefficient. Or sometimes people also use Chessie's coefficient. This equation is also similar to Cutter's equation, except that C is defined by this large value. So after this, you will get the actual mean velocity, which we can call it V. So if this actual mean velocity and critical velocity is same, then that is your trial depth. That is your depth and the area which you calculated. So That is your design, final design. If suppose V and V naught do not come same, you have to repeat it with a different depth, and you have to keep on repeating this process until V equal to V naught. So obviously in this there are a lot of